Hi everyone, I'm Josemary from Molecular Cloud, and today we're interviewing iGEM Aachen, and they will be telling us more about their project to develop a bioreactor which can develop cyclic ATP regeneration. So please tell us more about yourselves and your project.
Yeah. Hello, my name is Pia and I'm studying now 5th semester of the bachelor and I'm 22 years old.
Hi.
I'm Florian. Okay, sorry, please Lina.
Oh, you can go, it's fine.
Okay, then hi, I'm Flo. I'm studying mechanical engineering and business administration, also in the bachelor's.
All right, hi, my name is Lina. I'm studying biotechnology in my 5th semester and I guess I'm 21 years old. Yes, I think that's right.
Yeah, same goes for me. I'm also studying biotechnology in the 5th semester right now, and I'm 21 as well. And yeah.
Hi, I'm Selma. I'm 19 years old and I'm studying biology in the 5th semester, but I'm changing my major to biotechnology.
Awesome. Can you please tell us more about your project and, what led your team to create a bioreactor and how you're going about doing that?
I might just start with the main idea of our project. So our project is called M.A.R.S, which stands for Magnetic ATP Recycling System. And as the name already said, we want to do ATP recycling. So we want to recycle ATP to give it as a cofactor for different reactions. And because we want to make it more sustainable, we want to keep our little ATP factories by making them magnetically retainable. And I think what the actual issue or the problem is we want to tackle, I think Sven can tell you a little bit more about it.
Yeah, well, basically, when thinking about like new applications which might be viable in the whole field of synthetic biology, even before iGEM, we kind of thought about like cofactor generation might be quite a bottleneck for some industrial processes, and especially since ATP or NADH are both quite costly and expensive if you buy them and as a chemical, and therefore we thought about making cofactor regeneration kind of easier and how we could approach this. And since especially for NADPH and NADH, they are quite simple cofactor regeneration systems, for example using the glucose dehydrogenase, I think was it, which can recycle that. But especially ATP is quite tricky with how to do that. Some common methods are to do it with kinases and polyphosphates to recycle that. But we kind of wanted to go from a different approach, and also thought about making this whole synthetic protocell approach we're currently following might be something interesting, especially for the iGEM competition.
So is that the main mechanism behind your reactor?
But I can tell you more about the actual biological mechanism. So what we want to do is we want to create a kind of protocell, which definitely is not a living organism, what we want to create. So what we do is we need a hull, which is polymersomes, but for first tests, we try to do it with liposomes. And in this hull, we have two different enzymes. So the first one is ATP synthase, and the second one is bacteriorhodopsin. Bacteriorhodopsin is a proton pump. So when there's light, bacteriorhodopsin is able to pump protons inside our liposome or polymosome. And then the ATP synthase can use the protons to build ATP on the outside of our polymosome. So that's the biological thing. This is a little ATP factory, and we want to use anchor peptides, which are actually just some peptides that can bind different surfaces. We have one peptide that binds the polymersomal liposome, and then one that binds the magnetic particle, and then there's just a linker in between, and then we have our ATP factory connected to a magnetic particle. So they're going to be used in a little bioreactor. And I think Flo can tell you more about the actual bioreactor, because this is not my field of study.
You are muted.
Florian, you're muted.
Okay, so basically we wanted to use as much of the parameters in the laboratory as possible. So we thought, as Aachen is especially strong in shake flask methods, we would use that, especially also because then it's easier to get the light into the bioreactor. But still we wanted to scale the production as much as possible. Therefore, we used multiple shake flasks. Okay. And we will power the reactor by some electric motors and some timing belt. I can show you these things. They have some nice pins in it. And the great part about that is that it's commonly used in 3D printers. So it's basically available for a few dollars. So you can build the bioreactor on a huge cost savings. I think normal orbital shakers, they cost around at least $1,000, and we can do it for much less.
Yeah, so we have like the recycling part in two ways. So one way is like the ATP recycling, and the other way is also the regeneration of our factories. So it's like, yeah, in two ways we want to be sustainable.
So,
yeah, also,
no, go ahead.
Yeah, just one thing to add. The bioreactor has some magnets at the bottom of it to also mechanically get the protocells, which are connected to the magnetic particles, to the bottom of the flask, so we can pump the actual product that we want to use out at the top.
You can basically say like the biological part is more like the one we designed, and the bioreactor is more like the cherry on the top, you could say, which makes this like a simple and clever application where how to use this magnetic mechanism which is built into our system, and to provide this this usability.
So with all the generation of ATP, how has your team thought about what this would look like in a larger industrial setting, especially because the target is to reduce production costs for chemical and medicine production?
So I think in general, scale up is like one of the most difficult problems in biotechnology. Therefore, we thought in the beginning about designing like a special stirrer and put it in a big bioreactor tank. But the fact is that we can't really prognose at this point how the protocells will connect to the chassis, connect to the magnetic particles. So we sticked to parallelizing the process as much as possible, and then also again changing the environment of it. So basically, we also designed an automatization arm who puts the tubes of the pumps into the bioreactor and out again. So while we can't scale up the batch in itself, we can scale the throughput by automating basically the rest of the process.
So has your team designed, or so has your team spent any time directly in the lab? I know you said you've been concentrating on, using several flasks to make the project work. So have you been able to carry out your design as far as you wanted to?
Yeah, so for the biological part, we were in the laboratory since I think mid of June, something like this. So we had the chance to be there for only one person at the time. So it was a little bit difficult for us because most of the people are in the 4th semester, so we hadn't had so much experience in the lab. So at the beginning, it was a little bit difficult for us to be alone there. But then with the whole experience, it got better. And we concentrated first on the biological part, so building liposomes and also synthesizing the enzymes and getting everything together. And also we were in the FZ Jülich. It's like a research center apart from Aachen. And there we also wanted to test like one application. Maybe Sven can tell more about that.
Yeah, basically when the whole competition found its way to its end, like September-ish, we had the chance to expand our laboratory capacities a bit, since we had this new laboratory where we could sneak in 2 people, luckily, where we could do some additional research. And they are pretty focused on enzyme cascades. So they basically are very profound in vitro reactions and stuff like that. And we set our goal that we wanted to find an industrial application. For example, it was the carboxylate reductases, which are necessary for many pharmaceuticals because they synthesize aldehydes, which can then be converted to pharmaceutical precursors. That's where this whole pharmaceutical idea came from. And therefore we did several reaction kinetics and testings on how this system behaves with ATP, without ATP, and with the commonly used ATP regeneration system. Our big goal was then to also put in our chassis as well and see how it behaves, but sadly, the time and the circumstances were there, and according to this point, quite in our way. So we designed like a simulation model, which models this specific reaction with a simulation model of our system. You kind of get a grasp on how it would behave based on the data we could collect.
Yeah, therefore we also wanted to test because another approach is to use whole cells because they also regenerate and recycle the cofactors. But the problem with the whole cells is that if you have like toxic products or high concentrations, it isn't so good for them. So they won't work properly. And in addition, they also use the ATP for their metabolism. Therefore, we also wanted to show that our system could be like better than the common use with the whole cells, and that we also tested there.
Has your team taken any external initiatives to bring awareness or to issue how your project can be beneficial to this industry?
This part was like a big part of our project with the whole science communication. There we also had some meetings with the University of Costa Rica and also with the school there. We also had the chance to talk to some students in Uzbekistan and China. So we could spread our idea and also the whole awareness of the cofactor regeneration and also the need of such system for the production of pharmaceuticals in a sustainable and also maybe cheaper way. Therefore, we also participated in a podcast episode to also, not only to bring the topic to scientists or to students, but also to people from every scientific background, because we also wanted that they understand the need and that we can bring our idea to them.
Great. So is there anything else you would like our audience to know about your project?
Maybe it would be nice to say that this year was really special, as probably everybody knows. So what we did this year was to organize so-called little iGEM dates. So at the beginning of our project, we weren't able to actually meet. So we had all the meetings online. So what we did was to have a little schedule. So one person meets 3 other persons in a week, and we have like online meetings as well, but it was from person to person to spend at least 15 minutes with the other person to get to know each other. And I really like that. And even now at the end of our project, I think the last weeks were hard and really exhausting, but I think it's nice to have like a team and to spend a lot of time together and to just make the best of it.
Yeah, also the whole new situation with the with the online communication is quite, like, I had this funny story with the lab group. We were at our meeting and one of our team members is in the Master of Biology, and he's so like the expert, I think, for some techniques. And we had, I don't know what we wanted to do, but he suggested
we want to prove mitochondrion and ATP synthase. That was for the validation of both of them.
Yeah, and then he suggested the technique FAX, and we thought that he is mentioning, like, I don't know how to explain, like the old-fashioned printer, I think. So when you send it like to the phone number, and then this paper is printed at home for you. Yeah. And everybody like bachelor students thought that he is mentioning this like printer for at home. And we were saying to him, do you think that works? Because I don't know that this printer is going to help us with our cells and mitochondria. And then he was saying, your bachelor students, I meant like this method, to see if there are mitochondria in our solution. That was quite funny. And I think in like the real meeting, this wouldn't happen.
Well, I'm glad that, you know, your team made the best out of the circumstances and you made the initiatives to still build, you know, connections and communicate effectively, like weekly, and getting to know each other. That's very important.
Definitely.
Yeah. Well, iGEM Aachen, thank you so much for meeting with me today. Good luck in the iGEM Jamboree. It's our pleasure. Thanks again. Good luck again.
Thank you.